Hey guys, this is Mrs. Lyons. I promised a couple of people that I would make a video showing how to do calculations using a heating curve. So I'm going to work through this problem. This is the longest problem you could probably have, because if you read the problem, you will see that what happens. Whoops, I didn't mean to do that. What happens is what we're being asked to do is start with 20 grams of ice at minus 25 degrees, and we're going to heat that until it's steam at 125 degrees. Okay, so we're going all the way from ice to steam. All right, so the key thing here is to figure out what formulas to use and what constants to use at what point in time. Okay, so this problem starts at minus 25 degrees Celsius. So if I look at my cooling or my heating curve, excuse me, minus 25 is about right here. Okay, so what that tells me is this, I'm going to call this leg one of my calculation. Okay, because we want to figure out how much heat it takes to take 20 grams of ice and make steam out of it. Okay, so that's going to be our first leg. The other thing that you should do when you're looking at these problems in general is just identify what your end point is. So in this case, our end point is positive 125, which I'm going to say is right about here. So if I draw a not very straight line over, oh my goodness, it's a horrible line. Let's try again. So if we draw this line over, what we're going to find is that this leg here is our final leg. Okay, so what that means is we're going to have to do calculations for all 5 legs of this heating curve. All right, so let's just start. Okay, so for leg 1, all right, leg 1, we are looking at this piece of the cooling heating curve right here. All right, so for leg 1, our Q, remember Q is heat, and our heat is always going to be MC delta T, okay? But we have to figure out which ones of these equations we're going to use, okay? So I'm going to look here at my table, and I know that along this segment, the temperature is increasing. So that means I have to have a delta T. I have to have a temperature in my equation. All right, so that narrows this down to these 3 equations right here. And notice that these 3 equations are all the same. It's Q equals MC delta T. The difference is the C, the specific heat capacity, is different for liquid, gas, and solid. All right, so since we're starting with solid ice, okay, we are going to start with this equation. Q equals M times specific heat of a solid ice, delta T. And that tells us that our C, okay, our specific heat of our solid is 2.11 joules per gram degree Celsius. All right, so let's write this in here. All right, so Q is equal to the mass times, and I'm going to do C, and then I'm going to do solid. Okay, so specific heat of a solid times delta T. So instead of delta T, we know that delta T is equal to T final minus T initial. Okay, so that'll help us figure out what that delta T is. Okay, so let's look at some numbers. So Q is equal to M is the mass. So the mass is given in our problem. It says we've got 20 grams of ice. That mass doesn't ever change, all right? So we have 20 grams of ice, and we're going to multiply that times the specific heat of the solid, okay, which we said is 2.11 joules per gram degree Celsius. Notice I'm just typing the numbers in here right now. I'm not doing any units, just to save space and time. All right, and then times our delta T. Now, this is where it's easy to make a mistake, all right? We're looking at the change in temperature just for that leg of our graph. So in other words, we're looking for the delta T from minus 25 up to 0, okay? Because 0 is where that leg ends. So T final is 0, and we're going to subtract a minus 25. So if you do your math, that means that it's a positive 25. Okay, so I'm going to plug these into my calculator. So I have 20 times 2.11 times, and I'm just going to type it into parentheses just like I have it, parentheses 0 minus a negative 25, parentheses. 1055. So I get Q is equal to 1055. Our units are going to be joules. Now I'm just going to check that calculation again here real quick. So 20 times 2.11 times 25. Yes. Okay. So that's leg 1. And I'm going to move that up here a little bit because we've got to get 5 legs in. I think we can do it. All right. Leg 2. All right. Leg 2 of this graph is this leg. Okay. And notice that along this leg, there's no change in the temperature. The temperature is constant. That flat line tells us we've got a constant temperature. Okay. So that means we're going to need an equation that doesn't have a delta T. So that means we've got to use one of these 2 equations. Okay, and the way that you figure that out is you look at what's happening at that point on your heating curve. And in this case, this is where we're having the phase change between solid and liquid, which is we're going to use heat of fusion for this equation. All right, so we're going to use Q equals M times heat of fusion. Okay, so let's plug that in here. So leg 2 is going to be mass times heat, and I'm just going to make this a little F, heat of fusion. All right, so Q, I should do this. Hold on, let's do this. Q is equal to M times heat of fusion. So let's plug in some numbers. Remember, our mass never changes. For a problem, the mass is always going to be the same. All right, so we've got Q is equal to the mass times the heat of fusion, which is 3,355. So if we do the multiplication, that tells us that Q is equal to 67,100 joules. Right? Now, leg 3. Whoops. Okay, leg 3, we're just following this curve, okay? Leg 3 is another one of those places where we have the temperature increasing, okay? So we're going to go all the way through leg 3 because we're going to start at 0 and we're going to work our way up until 100 degrees. That's where we see boiling start, all right? So leg 3, we just have liquid in this segment. So we're going to look for the leg that has the specific heat of a liquid and then the constant. All right, so for this equation, for this calculation, we are going to do Q is equal to, let's see, what did we say? Mass times we're going to do the liquid, so heat capacity, specific heat of the liquid, times delta T. And I'm going to do it the same way, T final minus T initial. All right, so Q is going to equal our mass, so 20 grams, times the specific heat of a liquid, which is 4.18 joules, times temperature final minus temperature initial. So temperature final is 100 degrees because that's when we reach the boiling point. Initial temperature was 0. All right, so if I plug all of this into my calculator, I will get, let's do this, 20 times 20 times 4.18 times 100. So I get Q is equal to 8,360 joules for leg 3. All right, leg 4. What's happening at leg 4? Leg 4, we have leg 4. I'm struggling to get my highlighter. Silly thing. All right, leg 4 is again another plateau where we see another phase change. This time the phase change is from a liquid to a gas. All right, so we're kind of getting narrowed down on our equations, but remember that we've got the flat part of the graph, so that means there is no change in temperature. So we're going to use the equation Q equals mass times heat of vaporization. Vaporization is boiling, okay? So let's go down here. So leg 4, we're going to say Q is equal to M times, oh, not times C, M times heat of vaporization. Okay. So Q is equal to 20 grams times, what is our heat of fusion? Or excuse me, heat of vaporization, 2,260. All right, so our total Q for that leg is equal to 20 times 2260. 20 times 2260, 45,020. 45,200, sorry. 45,200 joules. Last leg. We have just enough room, maybe. Let's, you know what, let's do this last leg over here. So leg 5. At leg 5 is, if we look at our graph, for leg 5, we are starting at 100 degrees and we're going up to, what is our final temperature? 125. So this is where we've got gas, only gas, and we're going from 100 to 125 degrees. So we're just heating the temperature of the gas. Okay, so once again, we're going to look at our equations. We're going to find the one that has gas in it. Okay, and that's the equation that we're going to use, as well as the heat capacity. Okay, so let's do this. Leg 5, our equation Q is going to be equal to M times C of gas this time, times, and we're going to do delta T, so T final minus T initial. All right, so Q is equal to mass, so 20, times the specific heat of a gas, which is 2.00 joules per gram degree Celsius. And then our delta T, T final is 125 degrees. T initial is 100 degrees. Now, if we look at that, let's make sure we know why. Okay, because this segment Okay, segment 5 starts at 100 degrees. Okay, and then it works its way up. Okay, so that's why T initial is 100. All right, so let's see what Q is equal to. Q is going to be equal to 20 times 2 times 125 minus 100, 25. Is that right? So 20 times 2 times 25 is 1,000 joules. All right, so now we have energy for each of the legs. The final calculation we need to do is we need to calculate the total energy of this transformation. So we're just going to add everything together. We've got 1,055 plus 67,100 plus 8,360 plus 45,200 plus 1,000. Okay, now notice, I want you to notice a couple of things before we do this final calculation. Notice that we've got a couple of really big numbers. We've got 67,000 and 45,000. Okay, the one thing I want you to notice here is that all of these energies are different. We've got the exact same mass of material, but leg 2, it takes 67,000 joules of energy to take ice and form a liquid water, whereas it only requires 45,000 to take it from liquid to vaporizing it to form a gas. So it kind of gives you an idea that it takes more energy to melt ice than it does to boil water. Okay, so let's see, if I add all of these together, what am I going to get? So, whoops, I don't know what the N is there for. Hold on. Okay, so we've got 1,055 plus 67,100 plus 8,360 plus 1,000. Okay, so if I did my math right, which you can tell me if I didn't, I'm going to get a total heat of 77,515 joules. So that is our final answer. Okay, so to take ice all the way from minus 25 to steam at 125 takes 77,515 joules of energy. All right, I will stop there. I hope that was a little bit helpful in trying to figure out what